Paul Sutter is an astrophysicist at The Ohio State University and the chief scientist at COSI Science Center. Sutter is also host of Ask a Spaceman and Space Radio and leads astro tours around the world. But researchers have learned that those particles are much more complicated than that. That became clear when Otto Stern and Walther Gerlach shot some silver atoms through a varied magnetic field in 1922 and saw something they couldn't explain. The setup required silver atoms that were electrically neutral, with their electrons' charge perfectly balancing that of the protons. If you were to run this experiment and not know anything about quantum mechanics, a la Stern and Gerlach, you might expect one of two results. However, if the components of the atom were to behave like little metal balls that didn't merely have mass and charge but could also spin on their own axis, then that angular momentum would indeed interact with the surrounding magnetic field, producing a torque. This is a totally normal and well-known electromagnetic effect that you can try at home, assuming you have strong magnetic fields and rapidly spinning metal balls. Instead of going in a straight line, and instead of spreading out evenly, it appeared that the silver atoms had conspired to separate themselves into two distinct camps, with one group heading up and the other going down. The experimenters were witnessing one of the first in-your-face clues that the subatomic realm operates on rules that are far from the familiar ones. And since those atoms kinda sorta behaved as spinning balls of electrically charged metal, this new property was dubbed spin. And it turns out that spin has some pretty weird properties indeed. For one, the magnitude of a particular particle's spin is fixed. For example, a spin-a-half particle like an electron can only ever be measured to be plus a half or a half, corresponding to the up and down deflections of the Stern-Gerlach experiment. A spin-1 particle, such as a photon, can be measured to have directions plus 1, 0, or 1, and that's it. The length of that arrow is fixed for each kind of particle, but we're only ever allowed to measure a limited number of directions. If the arrow is pointing even slightly up, it will register in any experiment as plus a half. Good luck finding that restaurant. That right there is the bedeviling nature of quantum mechanics. It fundamentally limits our ability to measure things at small scales. The trouble stems from the approach that Erwin Schrödinger took when he went to figure out all this quantum business. But when Schrödinger wrote a relativistically correct version of his equation, he couldn't make heads or tails of it and abandoned it for the less correct, but still workable, version that we know and love. While incredibly useful, Schrödinger's picture of quantum mechanics doesn't automatically include any description of spin. It has to be inelegantly tacked on. But around the same time, a certain theoretical physicist named Paul-Adrien Maurice Dirac was also puzzling out the quantum world and went full bore with an approach to quantum mechanics that included special relativity. And unlike his buddy Erwin, he was able to crack the mathematical code and figure out its implications. His mathematics automatically included a description of spin. If he had worked it out a few years before the experiments of Stern and Gerlach, he could have predicted their results. Instead, we discovered quantum spin through experimentation, but Dirac taught us that, in order to understand this strange particle property, we have to put ourselves in a fully relativistic and quantum state of mind. Instead, spin is a fundamental property of our universe, manifested only in the intersection of quantum mechanics and special relativity, without macroscopic metaphors. It's only through Dirac's mathematical machinery that we can make predictions about spin behaviors that we need in order to do physics.